So in this chapter, we will introduce computational method and discretization techniques. To start with, the objective of this chapter is to develop ability to solve engineering problems in a numerical way and to evaluate numerical solution methods, knowing their advantages and limitations. We already discussed that CFD is computational fluid dynamics, and it's mainly based on transforming equations from differential form into numerical form. So we'll start to see what are the methods that we can use to do this. Okay. For example, let us consider the following case. In 1 second, I will zoom a little bit. Okay, so you have, let's say, this example. You have a bungee jumper, and you want to predict the velocity of the bungee jumper as function of time during the free fall. You can use analytical solution. In analytical solution, you will get the exact variation of velocity, and also you can use numerical technique. So our purpose is to just look at this simple example to see what is the strategy used in numerical methods. So, for example, to be able to do this, in this problem, we should determine the strength and length of the cord based on the jumper's weight and mass, and the cord will vary from jumper to jumper based on their size. And we have properties, of course, related to the person, the mass of the person, what is the cable property, okay, how much it can sustain tension, etc. So we should do analysis of the problem, and we should do sometimes if you do some assumptions, you can simplify the problem. So always try to simplify your problem as much as possible to have an easier solution. So for example, in the real life case, we have a lot of issues that can be neglected. And for example, you can neglect the weight of the rope, you can neglect resistance of air, or if it's considerable, because if you are jumping at large velocity, you cannot neglect resistance of air. It will be important. So, but you can, for example, neglect some sideways wind effects or relative motion of the jumper with respect to, you know that the jumper is not a particle. You can have motion of the hands relative to the body, but you can neglect these issues to simplify your model. So, if you want to perform an analysis, an analytical analysis, we'll start by saying we are interested into the velocity, and velocity is related to acceleration because A is dv by dt. So first, to be able to solve for the velocity function of time, I need to determine what is the expression of the acceleration. And then I should start with physics by writing the second law of Newton on the person. And I can simulate the person as a particle. And I put forces. So I have, let's say, I have the weight. Now, if I consider, I will simulate the person by its center of mass, G, and it's attached to the cable. So you have the weight and you have the tension developed. Of course, when the cable is extended, it will develop a tension. And when the cable is not extended, like here, it's still deformed, ما بيكون في tension. While you are jumping, you just have the weight and air resistance, okay? And the cable of tension will figure out when you are at the end of your fall. What I see the cable in tension completely, ما يعود deformable. You know that the cable can sustain only tension. It cannot sustain compression. Then you will have tension. But when you are studying the fall, the free fall, you have to consider the gravity. Will not call it free fall. In free fall, you just consider gravity. But here also you will take into consideration the air resistance, which is related to the velocity. So we know that air resistance is drag coefficient, okay, times velocity square. So we have a relation between air resistance and the velocity of jump. So now, if we use this information, okay, we will transform our physical problem to a differential equation. And the differential equation is mdv by dt equal to mg minus cdv square minus cd times v square. And if you divide all your terms by m, so here you have mg, if you divide by m, you end up with the following differential equation. dv by dt equals to g minus cd over mv squared. Now, how to solve this? To solve this, you have several ways. You can use analytical solution. So you can go to a differential analysis course, okay? You need, of course, a boundary condition. What you know is that at the beginning of the jump, the velocity is 0. So the boundary condition you have is that at t equals 0, the velocity is equal to 0. And from the differential analysis course, you can solve this equation. And this is the form of the solution. Already, for this simple problem, the solution is relatively complex. And here we were able to solve it, but sometimes we don't have analytical solution. So what we will do now, we will develop numerical techniques to solve this equation in a numerical way. Now you tell me, since we have an exact solution, why we will do the numerical solution? In general, when you develop a technique, to make sure it's working well, you compare it first with a problem where you have the analytical solution. Here you have the analytical solution, so you can see how the numerical solution can approach the exact solution. So we'll use this to develop our numerical techniques to see how we can improve the numerical solution. And once we get all of these skills, we can move to problems without analytical solution and use on them the numerical techniques developed here. So we can say that this is a differential equation. We want to transform it to a numerical equation. This means that I don't want to see derivatives. I want to see just like numbers, if you want. Okay. So instead of, we'll see how to deal with the derivative term. Derivative term will be approximated by delta v over delta t, where delta t is very small. Okay. And then we say that we are moving from continuous solution to discrete solution. Discrete means that we can get just velocities at some points, not at any point we want. And after getting several points, we can join them to get a certain profile. Okay, so we'll develop now together what are the different discretization methods that can be used to solve for the velocity function of time. Okay, so you remember that from calculus, the definition of derivative is limit when delta t tends to 0 of delta v over delta t. Now, of course, smaller is the time your time step, you will approach better the derivative. Okay, so if we take smaller delta t, we expect that the solution will be enhanced. But we'll see together also after that this is true to a certain extent, because numerical error, at the end of this course, we'll also see what are the different possible errors. We have round-off errors, we have truncation errors. We'll see that if you go for very small delta t's, it can affect in a bad way your solution. So you should develop techniques to optimize the value of the time step you take in order to not have divergent results. Now, let us try to deal with this term. And even delta v over delta t can be written in several ways. Why? Because, for example, if you have a certain point, let us call it point I, and you want to predict the derivative at this point, you can use in the expression of the derivative points before I, so point I minus 1. You can use also a point after I, which is I plus 1. So one of the methods is called Euler's method. Euler's method consists on taking point I with the point just after it and say that delta V over delta T is V at Ti plus 1 minus V at Ti over Ti plus 1 minus Ti. This is a first possibility. You can say, no, let me take I. This is called the forward method. We'll see that it's called forward method. You have also the backward method, which will use I and the point just before it. So you can write delta V over delta T as V at Ti minus V at Ti minus 1 over Ti minus Ti minus 1. This is also a possibility. Okay. No one will tell you that this is true and this is wrong. Both are possible. This is a numerical technique at the end. And you can approximate the derivative or by this method or by this one. Now, which one is more accurate? We'll see. We'll compare together the different techniques after. Okay. Now, also a possibility is to say, why not to take the point before and after? And this will be the central difference scheme that will introduce in a while. Okay. So now, but whatever we use, we were able to transform a derivative, okay, into a numerical calculation at some discrete points. Okay. So here you will get a continuous solution because you will get V as a function here. So this is the advantage of the analytical solution. The analytical solution will give you a continuous solution. It will give you V as a function of time. And you can get V function of T at any point you want. However, when you use numerical method, you get a discrete solution at certain specific points. Now, of course, it's better to increase the number of points to have better solution. But as I told you, to a certain extent, and if you have a lot of points, or also it's not good, because we'll see after that some errors will increase if you increase a lot the number of points. So now let us say we'll use Euler's forward difference method. As we said, in this method, we replace dV by dt by Vi plus 1 minus Vi over Ti plus 1 minus Ti. And then if you have in your equation V, you replace by V at point of interest, which is V at I. And then what the idea of the forward method is that you know V at I and you want to get Vi plus 1. So here, for example, we know that at t equals 0, V is equal to 0. So this is my first point, if you want. This is for I equals 0. I have V0 equal to 0. So if I replace in this equation, to start with, I start by point 0 and 1. Okay. So knowing the condition at point 0, I can deduce the condition at point 1 by writing that V1 minus V0 over T1 minus T0, and T1 minus T0 represents the time step delta T equals to G minus CD over M V0 squared. Now, you know value of V0, okay? So you can compute V1 function of V0. All you have to do is to multiply by delta T. So you can say that V at point 1 is equal to delta T times G minus CD over M times V0 squared. And you take V0 to the other side, so plus V0. So all you have to do then is to plug in this equation V0 by its value. You know the drag coefficient, you know M, you select a certain time step delta T, and you get V1. And now once you get V1, you will repeat the same procedure between V1 and V2. So V1 will give you V2, V2 will give you V3, etc. And the general expression of Vi plus 1, function of Vi, is that Vi plus 1 is equal to Vi plus G minus CD over MVI squared times Ti plus 1 minus Ti. Okay? Any question on this? Okay. Now, let us see, for example, okay, let us compare, if you want, we will compare together the analytical solution, which is exact, to the discretized solution. So let us say we considered a certain time step delta t. So in general, we fix delta t, so we don't vary it. Sometimes you can vary it with iterations, but it's advised to keep the same delta t from iteration to the other. And then you can compute velocities at different points. And once you get your velocities at different points, you can join these points and use fitting techniques, okay, to find an equation of v function of time. So you get an empirical solution if you want. And of course, since you have the analytical solution, you can compare with it. Okay. Now, let us go into detail again about for the different methods used for approximation of the first derivative. You can approximate the first derivative numerically using several methods. The first method, Euler's method, is forward difference. And as I told you, in forward difference, when you want to compute the velocity at a certain time, okay, you know that actually when you do dv by dt mathematically, this represents the slope of the tangent line to the curve. So if I draw the tangent line to the curve, then dv by dt represents the slope of this line. Now, what is the idea of forward difference? Is to say, let me do an approximation and consider that the tangent line can be approximated by the line joining, if you want, these 2 points. And when I join point ti to ti plus 1, so when I join point v at I to v at I plus 1, the slope of this line will be used to approximate the slope of the tangent line. And if you look at this figure, it seems that it's not very accurate here. You know why? Because you have a high delta t, a large delta t. And you can see already from the graph that if you take delta t small enough, so let's say now we take delta t much smaller. So let's say you have ti plus 1 corresponding to this point. So this is ti plus 1. So one of the first strategies to enhance the prediction of first derivative using forward difference is to reduce delta t. Okay. So by reducing delta t, look, these 2 points will be very close to each other. And now if you join them, you will really get a good approximation, because as you can see in the figure, for a certain value of delta t, as it approaches 0, then from the graph, it's clear that the 2 lines will be nearly coincident. So of course, by using very large delta t, you have large error. And as you reduce delta t, you are expected to enhance your prediction. Now, as I told you before, there is some unexpected issues related to other errors. We'll see that with computers, you always have round-off errors. And we'll see that round-off errors can cause some problems if you have delta t very, very small. بس بيكونوا كتير صغار delta t, يعني of the order of 10 minus a lot. Okay, for delta t small, reasonably small, you are expected to enhance your solution. And we'll see together when we deal with errors chapter that you can find an optimal value of delta t that will give you a good prediction of the derivative with minimal error. Okay? So this is the first method, which is the forward difference method. Now, another idea will be to take the point just before. So this is called the backward difference method for computation of the first derivative. So the only difference is that instead of taking points I and I plus 1, you take points I and I minus 1. Now, what will be the difference and how the error is affected? We'll study this together in this chapter. Okay? So here, also same idea. If you take delta t small enough, the 2 points will be closer to each other. And if you join the 2 points, you will get a good approximation of the tangent line. So by getting the slope of this line, joining points vi minus 1 vi is equal to delta v over delta t. So this is point I, this is point I plus 1. By joining these 2 points, I just say that the slope of this line is delta v over delta t. So it's v minus vi plus 1 over ti minus 1.